Now we move on to 8.3 and try to look at first general property of the waveguide solution. Now we'll go back to just the TMO or TE and either one have similar property. So we'll put them. Let me talk about them together because TMO is transverse magnetic field. So EZ is 0. EZ is not 0. Okay, and you go back to 8.26 A and B, and you can simplify that. E sub t will be equals to I, and then we define a symbol, a notation gamma square. Gamma square is just the denominator in the equation, which is omega square mu epsilon minus k square. Right. That is in 8.26, so you have that in the denominator. And for this case, for the TMO, you just have K times grad T easy. Right, so that should be Jackson's equation, except that Jackson now changed the convention, put a plus and minus sign, and consider K as positive, but you can always say that you use the convention, K has a sign, so it can either be positive. Okay, and then for this case, B sub t is B sub t is like the other way around. It's I 0 omega cos easy by gamma square. Okay, so that's just a simplification, just using the fact that BC is 0 to simplify these two equations. That's fine. And then with this simplification, you also have a relationship between BT and ET, which is very obvious, and which is not obvious from the original 8.76 because with both EZ and BC terms, you don't get a simple relationship. But now with this, for the TMO, so you obviously you see that there's similarity. You have I grad T EZ, you have the omega square. Here you I grad T EZ omega over gamma square, right? So you can substitute this into here. So that make it the rest is you have a K, you have mu epsilon omega square. Mu epsilon omega, just omega, not omega K. And then the rest is just right. I mean, in Jackson's 8.31, he used H sub t. H sub t is just B sub t divided by mu. If you divide it by mu, just basically cancel this. The mu will get you a H sub t. And Jackson used the notation of these Z factors and write it in the form of 8.31 with Z defined by 8.23 depends on whether it's TMO and TEMO, but that is just a simple substitution. So you can. The only thing you need to know right now is this is just there's a relationship between BT and ET by just BT is Z cos the BT component. So, so another way to look at it, BT is perpendicular ET in this case, and also obviously perpendicular EC. Okay, so the TE mode is similarly, you can do the same thing. TE mode.
When you subscript in the want a K in the
This one has, the denominator absorbed in here.
The K will be, if we want it to be divided by K, because we take it.
Oh, you multiply by K, yeah. IK, this IK, so you need a K here, you divide it by K. Yeah. All right, so now the TE mode is EC is 0, BC is not 0. Okay, so then you do the same thing. Now is and give the second term so minus omega cos grad T BC, and then BT is a gamma square K grad T BC. Right now, the relationship between BT and ET, you can like substitute BT in the here. I mean, this is like the BT, right? Or you can the other way around. If you want to express BT as ET somehow, then you can do another cross product of Z cos into this one, right? Z cos into E sub T is Z cos into this as a factor, and Z cos grad T. So it's triple product. The first term is along Z, but it's Z dot in the grad T, which is 0. The second term is minus sign. It's Z dot Z in grad T BZ. Z dot Z is 1, so it's minus of grad T BZ. And minus cancel with that, so I omega grad T BZ. That's which is like this one. So again, you substitute that into here. You have I grad T BZ. But you have an omega here, omega. You also have so you divide it by the omega. So you have K divided by omega. And now you have a Z cos T. Z cos ET. Because Z cos ET is goes to this one. You got T is this one divided by omega. Right, and then you get the K. Right, so that is similar. So again, you can also express this as h sub t. You don't have to be. You can follow Jackson. The only difference is that these two, one is omega over k, the other is k, and you have this mu epsilon for bt also. Okay, so there's some differences, but they are same. Okay, so we probably will not be able to get to 8.4, but the general dispersion relation is just the same. So we can describe that quickly. The equation to solve is 8.19. Now you this gamma square. Define as here. Define as here. Now that operator. Or any component is 0, but in our case, we just want to solve easy for the TE, for the TMO, and BC for the TEMO. And that can be done. obviously. And the idea is that we can solve for this subject to any the boundary condition for TE mode. The boundary condition is easy. Easy is 0 on the surface. This is partial B is 0. Partial N is on the surface, subject to the boundary. So this becomes a boundary value problem, right? And the idea is that the boundary value problem may not have solution. The only solution will exist for some discrete value of gamma. So not all gamma will support the solution. Okay, so you can indicate a solution of gamma is gamma lambda. So, gamma lambda square, and that is omega square is assumed to be given the single frequency you want to excite the wave with this omega. So the mode is now in the wave number k lambda square. Right. And so this is gamma sub lambda is given by the solution. So whatever the eigen solution, eigenvalue, that's will make the solution possible. That's this gamma, right? And the idea is that there's some kind of a uniform shape. So you can solve for omega, right? Omega square is now is just gamma lambda square plus lambda square. Or the other way around, you can solve for k lambda. K lambda is square root of mu epsilon times omega square. I mean, if you take the square root, then it's square root of omega square minus gamma lambda. Right? And so there's a figure in injection that you plot k. This is k lambda, and divided by this square root of mu epsilon. This is omega, and you see that with omega. Actually, I forgot this gamma lambda. Actually, that you need to multiply by mu epsilon. Multiply by mu epsilon, and that is defined as this omega lambda. This is so-called cutoff because omega lambda is greater. Gamma lambda. This is the cutoff frequency. So you see that if omega is less than the cutoff frequency, that is imaginary. The whole thing is imaginary. The wave is not propagating the mode. So this shape is a general. So this is general because if you divided this to the other side, or large omega, that is just. I mean, actually, if you divide it by omega, this will be 1 asymptotically, and this is omega lambda. And therefore, it's called cutoff because when omega is smaller than that, you don't have more. You don't have a propagating mode. Only when omega greater than that, but then you have more than one mode. Gamma omega gamma 1, gamma 2. All the lines are the same. It depends on what omega you're in. You can excite like 1 mode, but this one here you have 2 modes and 3 modes and all that. Okay. So the general shape of this dispersion relation is like that. And then how many number of modes you have depends on what the omega value omega is related to all these cutoff frequencies. Okay. And that's the general case. All right, and so next time, hopefully on Monday, we'll start solving the example the rectangular waveguide as an example how you solve for these all these cutoff frequency. Okay, okay, that's it for now. Any question?